Hey guys, BuildZoid here, and today we're going to be taking a look at a new measuring implement that I've made for myself for testing AM5 motherboards. So what you're seeing on the screen right now is the old method of measuring the core voltage regulation of AM5 motherboards, and this is basically just some coax soldered across a multilayer ceramic capacitor that's used for V-core filtering on the back of the CPU socket. Now, the obvious problem with this is that it's heavily affected by the power plane design of the motherboard. It also doesn't account for the impedance of the CPU socket, right? The CPU socket has quite a lot of resistance, relatively speaking, and some amount of inductance. I have no idea how much, because, yeah, that's not exactly convenient. Like, the resistance is pretty obvious. Like, you can just see the voltage drop across the socket, but the inductance, yeah, I have no idea. Just don't really have a method of measuring that. Yeah, so this method is pretty decent for figuring out if the motherboard is doing anything it shouldn't be doing. It's also pretty decent for sort of figuring out what load line calibration level has the least undershoot to some extent. For comparing motherboards, this is really not ideal. Like, it works if one motherboard is super duper terrible and another motherboard is way better, then this works fine. But if the motherboards are kind of similar in performance, then this is kind of useless. Um, so yeah, but now that I have a whole bunch of 9000 series CPUs, I decided to go ahead and take advantage of some of the unpopulated capacitor pads that AMD left on the 7950X to basically get measurements directly from the CPU package. So this accounts for the socket resistance. Well, not completely, but it accounts for the socket resistance a lot more than my previous method. You'll notice that I've decided to use capacitor pads that are as far away from the V-core VRM as possible. One interesting side effect of this is this seemingly measures even lower core voltage than what the voltage regulator itself is seeing, which makes me suspect that the core voltage sense point for 7000 series CPUs is probably somewhere around the middle of the package. And that is an actual concern. Like, I've seen it with GPUs where depending across the couple across a distance of a couple millimeters behind a GPU core, you'll actually have noticeable differences in voltage on the multi-layer ceramic capacitors. Which is one of the reasons why the 4090s have V-core coming into the GPU core from both sides, because it minimizes that voltage gradient behind the core itself. Anyway, so yeah, so this is just a twisted wire pair with a connector at the end, and then that plugs into some coax like so. If you're wondering what's with the aluminum foil, previously that coax was running very close to a voltage regulator and picking up tons of VRM switching noise, which makes the measurement unusable. So wrapping the coax in some aluminum foil was my sort of first idea for trying to fix that, and that kind of worked. But then I thought about it some more, and I realized I could use one of the microphone arms that I have to just support the coax in a position where it isn't near any voltage regulators, and that works a lot better. But at that point, I didn't bother to remove the aluminum foil because, it doesn't really hurt anything. So I just kind of left it there. Anyway, so yeah, so now I have core voltage measurements for AM5 CPUs, AM5 motherboards directly from a CPU, or directly from a CPU package. Again, we're not, we're technically a couple millimeters away from where the silicon actually is. So again, it's not going to be perfect, but it's a lot better than measuring from the back of the board. Yeah, so now we're going to take a look at some measurements with this, and ideally this should be very good for actually the other thing I wanted to mention is if you're wondering why I'm specifically using a 7000 series and not a 9000 series, it's very simple. With the 7000 series, AMD evidently hadn't figured out exactly how many multi-layer ceramics they need, so there's a bunch of empty pads just all around the CPU, right? There's just empty pads everywhere. On a 9000 series, there are no empty pads. There's just none. So apparently, like, they evidently figured out how many capacitors they need between 7000 series and 9000 series, and now there's no unpopulated pads. So that's a bit annoying. Like, so that's a bit annoying. So doing this with a 9000 series, I'd have to like desolder some of the existing capacitors. Also, the orientation of the pads on 9000 series is a bit changed a bit, which might make it more inconvenient to set this up. But yeah, also I don't really consider, like, at this point I have, a 9950X, and so the 7950X to me is kind of spare parts. So it's viable for these kinds of experiments. Anyway, let's move on to the oscilloscope and take a look at some measurements. So right now I just have the CPU running with the power management turned on, and you can see that at idle, we're like, the idle voltage is really, well, when the cores are asleep, the CPU is literally at like 300 millivolts. Right, so that's why like the CPU wakes up, because basically what we're seeing right now is the Windows event timer doing Windows event timer things. So if I just trigger on this, and I believe it runs at like 64 hertz. So every like a little over 16 milliseconds, I think it's 16.25, something like that. But yeah, so it's like a 64 hertz timer, and so every 16 point, I'm gonna go with 25. Somebody can correct me if I'm wrong. 16.25 milliseconds. Like Windows basically wakes up the CPU, checks that nothing's happening, and then it goes right back to sleep. And that's why we're seeing this waveform right now. Now, obviously, if I start moving the mouse, yeah, the CPU wakes right up. If you're wondering what's going on with the yellow line and the pink line, well, the pink line is the measurement from the CPU, and that's currently at minus 1.15 volts on the offset, whereas the yellow line is at minus 760, so that we can actually see the idle state, whereas the idle voltage, we can't see it on the pink trace. Anyway, I'm going to now put both of these into the same range. And what's really neat is I do actually have both of them set to the exact same voltage offset. So what's really neat is we're going to be able to see the like voltage step out like the voltages step apart relative to each other when the CPU goes under load. So, for some reason I don't have my windowed projector. Okay, there we go. So, for loading this up, we're just going to use Prime 95 because it's kind of convenient for running a whole bunch of different load scenarios. Yeah, okay, so we do have enough voltage range on this. So right now, you're like, this is just the power management doing its thing. Also, the gap between the yellow and the pink line is proportional to the amount of current flowing through the CPU socket. At least on average, it's proportional. Instantaneously, not so much, because there's going to be like inductance messing around with that, but yeah. Anyway, theoretically, you could calculate the current draw from the, like, if you knew the resistance of the CPU socket with like a high level of accuracy, you could calculate how much current the CPU is pulling based on the difference between the yellow and the pink line. But I don't know with a high level of accuracy what the resistance... Well, actually, I guess I could calibrate for that. So, like, I wouldn't consider it a high level of accuracy, but we'd get a rough idea of how much current it's pulling. Anyway, so first we're going to start with a very, very high constant, what I would consider like constant current load. So for that, I'm using an FFT size of 160K on both, and I'm disabling AVX512 because due to, well, for some... Actually, I'm not... For 160K FFT size, this isn't actually a concern, but Ryzen runs AVX512 cooler than it runs AVX2. And I think the reason for that, even when you're not hitting a memory bottleneck, like AVX512 is just slightly less current draw than AVX2, I suspect... Actually, the 9000 series might not do that, but 7000 series has the like half rate AVX512, So I suspect what's going on with that is like one AVX 512 instruction is actually takes up 2 clock cycles. So you have like one clock cycle where the instruction decode doesn't do anything because like everything's like you're still running the AVX 512 instruction anyway. Anyway, so this is like a constant current load. You can see that there's quite a gap between our CPU like back of socket voltage and our CPU substrate voltage, right? Like that pink line to that yellow line is, well, we're at 100 millivolts per division. I'm just going to pull up the cursors. We're going to pull them down. Also, you can see the power management, right? On like a millisecond time scale, it's adjusting the operating voltage of the CPU to eke out as much clock speed as possible. Wait, nope, that one's already where I want it. So yeah, we're seeing roughly about a 65 millivolt. Actually, they're not that well lined up. But yeah, like something like a 60, 70 millivolt voltage drop. And according to hardware info right now, the CPU is pulling, what's it pulling? Should be 160 amps. Yeah, 160 amps. We're actually bouncing off the current limit in this scenario. So yeah, we're hitting the current limit. So the CPU temperatures are actually quite low because we're at a very low voltage because this 160K FFT size, if we weren't hitting that current limit, pulls just stupid amounts of power. Yeah, because we do have that 160 amp current limit, the CPU actually hits that current limit at just 4.7 gigahertz. Actually, not even, right? Like you can see that it's not even really holding that. The good CCD is like trying to get to 4.7. The bad CCD is like trying to stay at 4.6. But anyway, so this is like a very high current load and a relatively constant current load because 160K FFT size is so small that it fits into the L3 caches of the CPU. So this isn't getting stalled out by memory access at all, and all of the spikes we're seeing is basically power management and Windows being Windows, right? The really tall spike is the Windows event timer that we were, like, at idle, it was waking up the CPU. In this scenario, it's not so much waking up the CPU as it's, like, pausing it every so often to go, like, hey, is everything running okay? So, yeah, so that's, like, the tall spikes over there. Anyway, I'm going to try trigger just on the event timer. And then we're going to zoom way in. And so what I find really interesting with this like substrate probe is that the overshoot on the substrate is basically the same height as it is on the CPU. Like the peak of that voltage overshoot is basically the same as it is on the back of the motherboard. I find that really surprising. I really thought that would be attenuated to some extent by the socket as well as the CPU substrate, but like nope, it's just bam. Like I mean there is a slight difference. It's very slightly lower. But yeah, I really thought that would get attenuated more and it really doesn't. So that's kind of surprising. At the same time, what's also interesting is that the undershoot, right, is kind of the same in both places, right? Like, obviously the lines aren't quite perfectly aligned. But, like, if we go to the bottom of this, so that's like 30 millivolts-ish of undershoot, and if we look at the bottom of here, it's also about 30 millivolts of undershoot, which I find really interesting because I thought the undershoot on the CPU substrate would be like significantly worse, but it's really not. It's like the same. So yeah, but that's obviously for like it to some extent. It depends on the scenario that you're testing in. Also, I do think the coax for the CPU socket or like the CPU substrate, we do still have what I suspect is some voltage regulator noise in there. Oops. Grab the wrong thing. Stay. And what I mean by voltage regulator noise is like these little squiggles right here. Because Because that is, yeah, that's like, I think the voltage regulator on this motherboard by default runs 500 or 600 kilohertz. And this is like, from here to here is like, what is it? Like 1.7, 1 point, that might be like 1.66 microseconds, right? What's 600 kilohertz? I want to say it's 1.66. The conversion between frequency and time, I am very bad at. I think it's 1.66. Yeah, so that's probably 600 kilohertz VRM. Getting in. Actually, we have one squiggle that's right next to this one, though. Then again, it is a multi-phase regulator, so we might be seeing like a couple different phases. Because what I've tried to do, like obviously you saw in the previous picture that I had like aluminum foil wrapped around the coax. That helped a bit. It was way worse earlier, like at one point. Like these little wiggles that I'm complaining about right now, these were like 20, like 100 plus millivolts tall. Like it was actually unusable for measurements because in my infinite wisdom, I just laid the coax flat across the motherboard and it just went right past the VRM and yeah, that was completely unusable. Right now, it is sort of being suspended above the motherboard, which mostly gets rid of the wiggle, like gets rid of the switching noise because it's just so far away from the voltage regulator at this point. But yeah, this board is kind of noisy. I've also used this probe setup on the Strix ITX board, and there this wasn't a problem. That board's VRM layout just doesn't cause these issues. So yeah, this board is like especially bad for this, and I've had the same problem in the past with Intel CPUs, where like some Z390 motherboards, because that's where like I first messed around with this kind of probing. I had like some Z390 motherboards have unshielded or partially shielded inductors, so if you run coax past those, it just spews VRM switching noise into anything that gets near those inductors. Those are absolutely horrendous. Funny thing is, these are, as far as I know, these should be fully shielded inductors, so I don't know how I'm having such a massive problem with like VRM switching noise getting into the signal. Yeah, it's like it's mostly gone at this point. And I don't think like that's not like, you know, it's like, well, that might be like 10, 20 millivolts, I guess. So that's annoying, but yeah. I guess we could try capture some more. Ooh, we had like a bunch of interruptions. And a big one. Anyway, I'll just let it run again. So now the thing is, in this configuration, actually judging, I mean, I'm not seeing anything super bad right now, but judging how good the voltage regulator is doing when the voltage is being dynamically adjusted is not very convenient. So now we're going to switch over to static core voltage. Actually, no, we're not, because I also wanted to show some other workloads. So that was 160k FFT size, and that I would basically consider a constant current load where it pulls like a very, like even, like right now we were smashing into that 160 amp current limit, but even if we weren't smashing into the 160 amp current limit, that is not going to get significantly noisier than what we just saw, right? Like the biggest transient during that workload is basically the Windows event timer doing Windows event timer things. Now, alternatively, you can run tests that are very, very memory starved. So instead of 160k FFT size, we're going to try, say, 640k. Again, with no AVX512. And you'll notice we're pulling less current, right? We're not, I mean, it's still a lot. We're not smashing straight into 160 amps, but you'll notice that our operating voltage is now significantly higher than it was before. And our CPU temperatures are much higher because the power draw is much higher. Like we're pulling less current, but we're pulling that current at a higher voltage. Therefore, the power consumption is much higher, and therefore the temperatures are much higher. Right? We're like, yeah, like the current is down like 10 amps, but the voltage is up like 20%. And this is what this looks like on the oscilloscope. So this just looks like a completely unintelligible mess because basically what's happening is the CPU is constantly, like, it executes some instructions and then it waits, and then it executes some instructions and then it waits, and then it executes some instructions and then it waits, and yeah, it just makes that. If we make the time scale a bit smaller, that doesn't really help. It's still basically an unintelligible mess. And if we try to, we should maybe, oh yeah, okay, so I'm gonna guess that's the Windows event. Yeah, that looks like some kind of, something interrupted the workload. Because we do still technically have Windows event timer spikes in this. I mean, that's something interrupting the workload again. At least, yeah, I'm guessing that's something interrupting the workload. This is so noisy that the Windows event timer is kind of getting swallowed up by it, by the looks of things. Because it should be, wait, no, we're still at too small a timescale because it's 16 milliseconds. No, it is actually getting swallowed up by it. I mean, this is probably Windows event time. Actually, no, that's a bit late for Windows event timer. Yeah, so this swallows it up. So that's fun. The CPU must be absolutely thrilled about what I'm doing to it right now. So, anyway, that's all core with a heavy memory bottleneck. Though, if we stop some of the workers, actually, I'm just going to stop all of them. Because I wanted to stop like half, but yeah, that evidently didn't work. Let's try 640 again. But we're going to run it on just... let's just run 6 cores, see how that behaves. Yeah, so that's a lot less bad. Also, that doesn't seem to be memory bottlenecked anymore. Like, we're seeing power management doing things, but yeah, we're not seeing the... That doesn't look like it's constantly stalling out on memory access. And that's not one of the funny things is, like, especially with the 7800X3D, not the... Like, 9800X3D pulls more power because AMD solved the, like, the thermal issues with the 3D V-cache. But, with the 7800X3D, I actually ran that as a CPU on the oscilloscope, and I don't think I ever made a video about it, because that CPU pulls so little current that from a motherboard power delivery perspective, it's trivial to deal with. Right? Because the thing with the, like, overshoot and the undershoot is those are directly tied to how much peak current the CPU can pull, because the overshoot is based on how much current you're trying to basically stop, and the undershoot is based on how much current you need to ramp up to, right? So if you have a chip that maxes out at like 60 amps, it just cannot produce as much undershoot as a chip that ramps all the way up to like a 200, right? Which like a 16 core Ryzen chip can do up to like 200, bit over 200 amps. Well, I mean, if you had a lot of cooling, you might be able to get up to 250, right? And that's just going to make way worse transients than something that maxes out at like 100 or 125, right? Because half as many cores, half as much peak current draw. And if you have a 6 core, it basically doesn't, like, the motherboard basically doesn't have to do anything anymore. Anyway, but in this setup, this is not really useful for, you know, comparing motherboard VRMs because the voltage is up to the whims of the CPU's power management, so we don't really know what the target voltage is. Oh, actually, I guess one thing I could have shown is... no, that's better when we're on static voltage. So in this configuration, it's kind of fun to watch because you can like see the power management and that kind of thing going on. It's not really that useful for actually judging motherboards against each other because the we don't know what the target voltage is, right? So obviously for that we want static voltage. So that's what we're going to switch over to now. And we're going to run the CPU at very low frequencies because I don't really want it to crash. And also I don't really want it to pull a ton of current, ideally, because, yeah, we are going to be running Prime 95 160K FFT, but now there's not going to be a power limit. We're going to use AMD overclocking mode, and we're going to set the core voltage to 1.1, which is very, very low because I am running Prime 95. And that 160K FFT size is actually ridiculous. And then we're going to set our load line calibration to mode 1. Now, MSI has this very useful and extremely misleading graphic over here about how this is going to boost the core voltage, which is not a thing unless you're measuring the core voltage from the back of the motherboard socket. So, yeah. Anyway, we're not going to change anything else right now because that's not really relevant to the video. And the point of this is basically we should see almost exactly 1.1 volts on both the coax, except for the the issue with the coax going to the oscilloscope is it's actually loading the signal a bit, so it's pulling the voltage down. Because there's current flowing through the coax, like a bit. It's not a lot, but there's a 50 ohm termination at the end, and then also there's like a ground level difference between the motherboard and the oscilloscope. And even if the oscilloscope wasn't grounded, there's still a ground level difference between the two connections. Like the ground on the motherboard is going to be slightly lower voltage than the ground at the CPU. So yeah, like ideally I would have active probes for this. But unfortunately, low voltage active probes are extremely expensive. Or you have to make them yourself, and I'm too dumb for that. Or more, well, dumb plus lazy. Because if I was less lazy, I could learn how to make them. Anyway, I don't think that's too much of a concern for these measurements. But anyway, so now, why is the voltage bouncing around so much? It shouldn't really be doing that anymore. Like, I'm not too surprised that the yellow line is going up. I'm surprised that the pink one is going up with it. That should not be happening. Oh, maybe it's because I'm in AMD overclocking mode instead of override mode. I'll also pull up some measurements now. So we're going to just look at average voltage for now. And also channel 3. Yeah, so right now, if we look at hardware info, yeah, so right now the oscilloscope's reading a little bit high by like 4 millivolts. The thing is, the oscilloscope does have the option to bias the inputs a bit. But I haven't I haven't set the bias based on this motherboard. This is the bias I used for this ITX Strix, and I need to like work around that to some extent. As in, like, I basically need to. I'm like I'm. I'm not sure, but I think I might have to set the bias based on each, like, for each motherboard individually. Um, but anyway, that's a concern for when I try to actually run comparisons between boards. So right now the scope is reading like 4 millivolts too high. Back of socket measurement matches the one that we're getting from the motherboard sensor, though. Then again, the motherboard sensor has... Actually, that doesn't seem that limited resolution. All right, so we have the V-core sensor from the Super I/O, and that looks like it's in 4 millivolt steps, which is a lot better than what I was expecting, because a lot of Super I/Os are like 12 millivolt steps, which is horrendous. Unless that's an average measurement. Please don't tell me I'm on average right now. No, that's maximum. Yeah, so it looks like it's in 4 millivolt steps. Anyway, this is generally going to be the most accurate sensor, and so the substrate probe should be matching that, ideally. So I'm going to set the... Yeah, so that's about right now. Yeah, so 1.05, 1.05, so those are both about correct. And I'm going to do the same for channel 1 just because... Just for consistency. I mean, the thing with channel 1 is that it's just going to be all over the place. Based on the output current. So anyway, let's now run some actual workloads. In the future, my plan for, like, doing the... Like, trying to get the... voltages lined up is to use a multimeter to check that the voltages are, like, check what the coax measures, like, as average voltage with a multimeter, without the oscilloscope loading it, and then, like, get the oscilloscope to match that value, and hopefully that value also ends up being pretty close to the SVI3 TFN sensor. Now, yeah, let's hit some actual workloads. So the thing is that and also I'll do that, like, sort of calibration step at idle, because at idle we don't have a lot of current flowing through everything, and if there's a lot of current flowing, then it's going to throw off the, like, the resistance of the substrate is going to affect things, like, the resistances of everything are going to affect things. So the voltage, like, basically we would expect the voltage everywhere to be the same if there's zero current flowing through the CPU. Now, I can't actually get the CPU to pull zero current. I guess I could downcore it to just one core. Or I could run it at like 800 megahertz. That would also get pretty close to zero current flow, for like a calibration setup. But anyway, yeah, and then hopeful, and then everything would be relative from that. But anyway, so let's run 160K FFT size now. And the thing I'm most sort of happy with is, like, seeing how like, at idle you can see how the yellow and the pink line are, like, right on top of each other because there's no current flowing, so there's not a lot of voltage drop across that CPU socket. As soon as we hit prime 95, those two are going to step apart. Actually, more like pink is supposed to not change and yellow is going to shoot up. And that's exactly what we see. Right, because with mode 1 LLC on an MSI motherboard, there's no V-droop. Right, so the voltage on the like, CPU substrate basically hasn't changed. It has technically gone up a little bit, right? You can see that now it's another couple millivolts higher than it was before. And if we look at the measurement inside hardware info, that actually hasn't changed. That's still 1.1105. But evidently that coax that's hooked up to the CPU substrate, like, that's really close to what the actual CPU is getting. Right, now if we look at the motherboard sensor, so the V-core over here, yeah, that's not great. The accuracy of that is not, like, that's wrong. What I'm surprised by is that V-core sensor is not as wrong as the measurement from the back of the CPU socket. Like, I was fully expecting it to be that. Yeah, evidently, and this is a thing that MSI has been doing on a lot of their boards now, is they've done something to try get the Super I/O sensor to be less horribly inaccurate. Because the cheapest way of implementing the Super I/O sensor is to just connect it somewhere on the motherboard power plane. And then at idle, your measurement is pretty accurate. But at high load, it's garbage because the current, like the voltage drop due to the current draw means that the measurement from the CPU, like from the motherboard's power plane, is just, it's just junk, right? But yeah, MSI's been doing something to sort of work around that. Not as intensive as what, say, Gigabyte and Asus do on some of their motherboards, where they literally copy the DiSense readings using an op amp to the Super I/O. MSI isn't doing anything that complicated. But it is nice to see that this is actually working pretty well. For comparison, there are some motherboards, especially like cheaper boards from Gigabyte and Asus and ASRock, where in this kind of scenario, that sensor would be reading like 1.2 volts. Also, right now we're pulling 186 amps because, yeah, 160K FFT size with no current limiting is intense. And let's take a look at what's going on the oscilloscope. I'm going to move the cursors back in line. I'm going to get the trigger out of the way so I can actually see it. So right now, the voltage drop across the socket is about 77 millivolts. Which core current is about 188 amps. So you could calculate how much resistance the socket has from that. With, I don't like, not, you know, I'm not, this motherboard does use smart power stages. So theoretically, that power reading should, like that current reading should actually be pretty accurate. But, yeah, not, though I'm not sure. No, it should be fine for this kind of thing. Anyway, let's take a closer look. Where's my trigger? And yeah, and what I find really interesting, again, is how, like, the overshoot is, especially on, like, the overshoot on the substrate is almost the same as on the motherboard. But what's even more interesting is that the undershoot on the motherboard looks way worse than it does on the CPU. Right? Like, like, that looks like, I don't know, what is that? That looks like 65 millivolts of undershoot. But if we look at what we're seeing on the pink trace, that's more like 30, which I find very, very surprising. Because I would have always figured that the undershoot would be way worse than that on the actual, like, CPU substrate. I would have figured it would be basically the same. Well, no, not same. I always thought it would be worse than what you see on the back of the CPU socket, but it's like, no, the back of the socket on this board actually measures worse than the CPU substrate does. So that's really, really surprising to me. Yeah. Anyway, one way to make the CPU very upset is to move the mouse around a bunch, because the mouse input needs processing that stalls Prime 95 out. So you can see that there. But yeah, so I'm like, so mode 8 is a lot less bad. I mean, not mode 8, but, well, we do get some massive undershoots, but I think that's like, let's try trigger on one of those. So what's going on here? Oh, I don't have enough too much, like, too high a time scale. I think that's an idle step. Like, I think that's, like, waking up, because it, like, this voltage level over here is much lower than what it recovered. Like, you know, we get this, like, Yeah, I'm guessing this is like something stalled the workload in this area, and then it ramped back up here, and so we get a lot of undershoot from that. For that one specifically, though, because there was some other ones that were really bad. Oh, well. Yeah, this one's worse. Because we have, like, pretty... Yeah, like, pretty... Yeah, like, no, this isn't idling, right? Like, there's a big gap between the pink and yellow here, and it's basically the same gap over on this side. And then we just have this massive undershoot down here. At the same time, though, it's interesting how, like, the undershoot isn't always going to be this terrible, right? Like, this spike's way worse than, say, this one over here, and that's basically the same event, or, like, a similar event. Anyway, let's go back to run mode. So, yeah, so that's mode 1. I was really, like, I'm still surprised at how, like, the undershoot isn't that much worse, and the overshoot is, like, basically the same. I am honestly kind of surprised about that. I kind of almost want to have a measurement from the actual like bulk capacitor bank of the motherboard. Because I'm wondering, because the thing is, like, the further away you get from the CPU substrate, like from the silicon of the CPU, the higher the average voltage level is going to be, but the smaller the gap, like the smaller the peak of the overshoot, relatively speaking. Right? So if we look at the overshoot end of this thing, like what I mean by that is you can see how like this voltage level, like the yellow line, is a lot closer to the peak of this than the pink line is to the peak of that. And so I'm thinking like, okay, well, if we measured from the bulk capacitors, would this spike, like the upward spike, would it basically just be the same level? And so the spike that we're seeing is less like an upward spike and more the voltage across the entire power plane just leveling out to what it is at the inductors or at the bulk capacitors, right? Where it's not. I don't know if I've explained that correctly, but that's sort of like what I'm basically visualizing is like if you think of the voltage as like a water level, right? You have like a low water level at the CPU. You have a higher water level on the back of the CPU socket, and then at the VRM you would have a very high water level. And so what I'm thinking is like, well, when the current draw drops, does it just level out to whatever it is at the inductors? Um, so that would be, I think that would be kind of interesting to try capture that because I suspect that's roughly what we might see, though it would also depend on the voltage regulator design. This motherboard does use some rather low inductance inductors, so there's also not going to be that much energy stored in them during a load release transient. So I wonder if you had like a very high inductance motherboard, if that would be worse. Um, Though I can't think of like the thing is when I think like high inductance motherboard, I'm thinking like DDR3 era because back then it was normal for motherboards to have like thousands of nanohenries for their vCore inductors, whereas these days we're talking like I consider Asus motherboards high inductance because they use like 400 nanohenries, which is nothing compared to what it was in the DDR3 days. Um, but anyway, so yeah, so that's that for a like a static load test. Um, Now let's take a look at what it looks like when the CPU is starving for memory access, because not particularly useful for taking measurements, but kind of fun to see the. I guess you could kind of say power delivery getting pushed to its absolute limits. So we're going to switch over from small FFTs to 640 FFT size on all of the cores with no 512. And yep, still gibberish. You know, looking at this result, this might actually be better for testing. The thing is, we're only pulling 105 amps right now. Like, I'm wondering, this might be better. Yeah, this might, so I might have to run both scenarios. Because the bottom of that spike is, like, still very, very low. Right? And obviously, if we ran this scenario with more voltage, because right now we're pulling 106 amps, right? And we're nowhere near being cooling limited. We're only at 65 degrees. So you could probably run this scenario at like 1.2 volts instead of 1.1 volts, and then it would look way worse. And it would still be very coolable. Actually, would it look way worse? It would definitely look a lot worse. I mean, let's just pull up a peak-to-peak measurement quickly. On channel 3, because I don't really care about channel 1 that much right now. So, yeah, that's a 200 millivolts peak-to-peak, and if we just run this, yeah, it tends to hover around that. So, I think with more voltage and more current behind this CPU complaining CPU complaining about not having enough memory bandwidth scenario, we might see something even worse. Also, I just love seeing the yellow line and the pink line like separate out based on output current. Yeah, it's just so cool to have such a clear representation of current draw. Even though I don't know how much current it actually represents most of the time, but anyway, so yeah, let's go up to 1.2 volts. Now, obviously, if we tried to run 160K FFT size at 1.2 volts, the CPU will probably actually just shut down. Because there is a thermal limit at 115 degrees Celsius where the CPU will actually just turn off. So we definitely cannot run 160K in that scenario. Also, I would hate to break my one probe 7950X. Because, yeah, that would not be good if the CPU broke. So previously, the 640 FFT size was peak to peak of about 200 millivolts. I'm going to guess it's going to be like 250. Might even reach 300, but I'm going to go with 250, I think. So let's go 640. Huh, still 200. So that's not that bad. Oh, the current draw really didn't... Oh, well, that does make sense. Yeah, I underestimated how much the current draw would change. There's like a couple bad ones that reach into the like 230 millivolt range. But the thing is, and it makes sense because I bumped the voltage by 10%, so it doesn't really make sense that the current draw would go up more than 10%. I don't know why I was thinking like, oh, I'm going to get it to pull like 160 amps. Nope, no, it's not pulling 160. It's pulling 140. So yeah, the peak to peak didn't get that much worse. Obviously can't run 160K FFT size in this scenario though. Anyway, so we'll stop that. So that did not go quite as planned, but that might be an interesting scenario to try test. Because it's a very, like, this is just pure noise, basically, from the CPU side, getting thrown at the voltage regulator. So that might be worth testing. Because I kind of suspect that the voltage regulator might have an easier time dealing with, like, a one-off, you know, oh, the workload got interrupted type thing, compared to the CPU is having, like, a seizure, basically, in terms of current draw. So anyway, now we're going to go to voltage levels that aren't going to burn my CPU because we do want to go back to 160k FFT size. We're going to switch over to mode 8 LLC. And now obviously we're going to get some voltage V droop on the pink trace, but what I really like what I want to show is how they now like the yellow is still going to go up though and pink is going to go down. So I just think that looks cool. We're not going to actually try to do some comparison measurements right now because, again, while the video is long enough as is, though this is another one of those MSI motherboards where even the highest LLC just doesn't have that much V droop, right? So actually, I wonder if well, no, because our voltage is lower. Average voltage is going to be lower. Yeah, you know what? I'm throwing 640k at it anyway, just because I'm kind of wondering what will happen. I don't think it's a fair test, because if the average voltage is lower, the current draw is lower, therefore, you know, there's going to be less peak to peak just because there's less current behind it, but, yeah, anyway, let's start with 160k. Yeah, and so you can see how the voltages, like, step apart. And there's now, so obviously the voltage we actually set is 1.1 millivolts, and now there's like 50 millivolts of E-droop, as you can see. That reading right there. Interestingly enough, yeah, like that V-core sensor on this motherboard is not that inaccurate, which is pretty neat. It's not perfect, but it's like, I think I've tested at least one X87 motherboard where that V-core sensor is off by like 100 millivolts under load. At idle, it's fine because, you know, but under load, it's just way off. Anyway, yeah, so we have 1.05 on the die sense from the CPU, and the oscilloscope is like, yeah, man, I'm so surprised at how well that like connection to the 7950X works. It's so close. It's off by like a fraction of a millivolt. Now, admittedly, that is after me manually biasing it, so, you know, but like still, even if I didn't adjust it by 6 millivolts, it's so close to what the CPU is actually getting. So that's really cool. Instead of like the back of socket measurement, which is off by like 70 millivolts. So yeah, I am very pleased with that. And then in terms of undershoot, unfortunately, I don't think this is going to be much of an improvement over what we were seeing with, even with mode 1. Yeah, because there's still not that much V-droop here. Though I guess the funny side effect of that is that, yeah, you can just use mode 7 or mode 8 LLC on this motherboard and it, you know, there's not really any downsides to it. Yeah, but now when you, like, now when the mouse, like, interrupts the workload, you can see how the undershoot goes away because the current draw drops. I mean, not undershoot, but the V-droop gets removed because of the current draw reducing. Anyway, let's try 640k FFT size. Because I wonder if this, like, it should be a little bit lower peak to peak, but I wonder if it's going to be, like, just the current draw is going to lower it, but I'm wondering, like, if we'll see more of an improvement than that. Oh, maybe we do. Because that's, like, 150? Oh, I might need to go off of the average measurement for that. And the average voltage is not that much lower. I mean, we could try this at, like, high voltage. We could try this at 1.2. Oh, and then the lines come together again as soon as the current draw is removed. I like, on the funny thing is, my initial intention with this probe was like, oh, I'm not gonna have to solder coax to the back of a motherboard anymore. But I find it like the getting to see the two, like, how the two voltages react to current draw relative to each other is kind of cool. So I might keep soldering coax to the back of the motherboard anyway, even if I ultimately don't judge the voltage regulation performance based on that. And we do have a bunch of E-droop, so I'm actually going to go all the way up to like 1.225. Because that would actually be really interesting to me if like Mode 8 LLC had a big advantage in like a very noisy scenario, but not a big advantage in like a very constant current type load. And I guess different motherboards might react differently as well. Because I'd say the MSI, like the Tomahawk here, the capacitor configuration, in my opinion, is kind of minimalist compared to some of the other motherboards that exist for X870. Like, ASRock is going completely ham on the bulk capacitance. Normally, motherboards use 560 microfarad capacitors and like a couple of them. And for the X870E Taichi, ASRock is advertising 1,000 microfarad capacitors. And they're not there's like a capacitor per phase on that board, right? This board, I think, has like 8 bulk capacitors. The Taichi probably has like 4 times the bulk capacitance of this. Okay, maybe not 4 times, like 3 times, right? And like my initial reaction to that is it probably doesn't do anything because all of that is in through-hole capacitors, and through-hole capacitors have so much equivalent series inductance that they may as well be useless past a certain point. But I do wonder, and that's kind of one of the main reasons that I've made this probe. Well, the other main reason. And then, of course, you have Asus, where actually for X670, Asus was going really heavy on the ceramic in the back of the CPU socket, but then kind of minimalist on the through-hole capacitors. Like, some of those boards have like 4 bulk capacitors, and then everything else is just like, and then there's just a ton of ceramic behind the CPU. But with X870, they've actually lightened up on the amount of ceramic that they're putting onto their boards. So, yeah, like, I do wonder what kind of effects those those design choices have, if any. Because that's the other real, like, that's kind of the frustrating thing for me with measuring a lot of motherboards is a lot of the time you find that there's no difference. Even though you have, like, drastic differences in, like, capacitor configuration and voltage controller manufacturer and inductors and power stages, and then you measure them and it's like, oh, these are all the same. But I guess the nice thing about like, hey, these are all the same is like, well, at least you don't have to spend a bunch of extra money for, you know, a ton of extra capacitors that don't actually do anything. Whoa, so Mode 8 really does seem to be just better in this like very noisy scenario. Huh. I mean, you know, again, we've got like a peak somewhere in like the 230, but I'm pretty sure in Mode 1 we were peaking all the way up to like 300 peak to peak. Now, one annoying issue is if I move the mouse around a bunch, that's gonna... Oh, that doesn't really... Well, I guess, yeah, because if in Mode 8 the voltage regulator is just better at reacting to sudden load swings, then moving the mouse around isn't going to upset it so much. Again, we're a little bit low on the average voltage again, right? 1.18. So evidently I could have given it more voltage if I wanted to hit 1.2 average. But yeah, so I am super excited about this new probe because it works so much better than I thought it would. Like, its one weakness is if the coax gets too close to a voltage regulator, and then it just picks up VRM switching noise instead of CPU noise. Yeah, like I was really worried that this was just like it's just gonna be way off again, like it's gonna measure high. But no, it measures basically what the CPU is seeing. And as long as I don't lie it flat on an inductor, it works great. Like, um, Yeah, so I am very happy with how well this is working. It was really annoying to actually produce, or well, produce. Yeah, like it was kind of annoying to make because the thing is, like, you'll notice that there's like little red gel over the capacitor pads. That's solder mask because yeah, these pads are tiny. Also, soldering directly to the CPU substrate sucks. I had to heat the CPU to like 120 degrees Celsius. Because those pads are so small that like, and they're on a main power plane, right? So like, getting any heat into those pads is awful. Um, so yeah. Also, I glued the wires into place. If you're wondering what's with that clear stuff, that's not flux. That's glue, so that it doesn't like because yeah, the connection is super thin. So that's just to make sure that it doesn't break off. Um, But yeah, I'm really pleased with how well this is working, and I'm honestly kind of surprised with how well this is working. So anyway, wanted to just show that off because yeah, I think it's neat. Um, and yeah, that's it for the video. So a big thank you to the channel supporters for making videos like this one possible. Um, Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon and a Spring store and a whole bunch of other links down in the description that you could check out, and that would be much appreciated. And with that out of the way, thanks for watching and goodbye.